next talk is pre-recorded. So we will have Elmar Jürgens, who works as both as a researcher and founder. Today he will be talking about test intelligence for and with the robot framework. So let's enjoy Elmar's talk.
As testers and test automation developers, we faced with the challenge. We need to test more and more functionality in less and less time. More and more functionality because successful software grows and we keep adding new features. Less and less time because release cycles shorten. And this forces us as a discipline to be more effective and efficient because we can't, for every single release, keep manually performing every single test case. And also for automated tests, we see more and more teams for which every single time running the entire test suite doesn't work because the test suites have grown to a size that makes that unfeasible. Some of the customers we work with have tens or hundreds of thousands of automated tests, and it takes them weeks or sometimes months to execute the entire test suite. In this presentation, I want to outline test intelligence analyses that help us be more effective and efficient by bringing transparency into the black box of software testing. What do I mean by bringing transparency into the black box of software testing? To start with, I want to show you two examples from other disciplines, which you know already. The first one is X-ray pictures. This is a picture from a broken kneecap. More specifically, this is my right kneecap. I broke it a couple of years ago in an accident. And the bright white lines you see are the steel wires that bring together the broken pieces of bone. Why do I have that in here? Because after the surgery, I had to go to a doctor, and effectively that doctor performed quality assurance. And what was striking to me was that the doctor didn't ask me how I feel and didn't take my blood pressure, but he simply took an X-ray of my knee and only inspected those bits of my body that the surgeon had changed. And I found that very effective. The second example is a heat map from a football match. In this case, from a Champions League semi-final between Bayern München, my club, and Paris Saint-Germain, which unfortunately we lost. And on the heat map, you see which players spent how much time in which areas of the field. And I don't want to take the sports metaphor too far, but I find it ironic that for free, as a football fan, I get more information about where my players spent their time than I have as a person who is responsible for a mission-critical software system in many cases, about which tests execute which parts of the system or which testers inspected which functionality of which feature. And if we had that information as testers, it would allow us to be more selective in which tests we execute at which time. The goal of my presentation is to show you which test intelligence analyses can provide similar information. Similar to the doctor who saw which parts of my body were changed in which way, or similar to the heat map that shows the football coach which players spent which time where. These analyses can show us as testers which changes were performed by the developers and are more error-prone than other areas, and which tests execute which parts of the code, so that we can be more selective when we execute them. The remaining presentation consists of two parts. In the first part, I want to focus on the data sources that we can analyze. And in the second part, I want to highlight 3 questions we can answer with this data. Some background on me so that you know where the experiences come from that I present. I hold 2 professional roles. The first one is as a postdoctoral researcher at the Technical University of Munich. And in this role, I'm interested in which things we can measure about software are really relevant to know, and which, for example, test selection strategies really work. Because unfortunately, in software measurement, we often focus on what is easy to measure and not what is relevant to know. My second role is that as a founder of CQSE, We build software analysis and software intelligence tools. We are a spin-off of the Technical University of Munich. We are 12 years old now, have 50 full-time employees, 47 of which are computer scientists, and 22 of which hold a PhD in software quality analysis. And in this role, I'm interested in impact, how the analyses and tools need to look like so that they really have a positive impact in practice. And I look at test intelligence from both perspectives. The first data source I want to focus on is the version control system. Version control systems like Git, Subversion, or in some cases still CVS, contain the entire version history of the system. That means they contain the source code, but also all the changes that were made between the versions of the software system. And we can use that to compute what changed since the last release. And I like to look at that information and to display it in presentations in form of a so-called tree map. This is a tree map of a business information system, 1.5 million lines of C# code. And a tree map displays software artifacts as rectangles. The big white rectangles are components. The small black rectangles are methods or functions. And the tree map renders the software artifacts in such a way that the surface area of the rectangle corresponds to the length of the method in lines of code. And the colors depict the following. Gray means unchanged. In this case, 30 developers worked for 6 months, and this part of the system didn't change or hardly change at all. The colored boxes are the edit in new code or modified in new code. Orange means modified, red is new code. So here at one glance, much like the X-ray picture, we see in this area there were a lot of changes, in this area hardly any. This is the change tree map for the robot framework between versions 4.1 and 5.0. Same color semantics. Gray means unchanged. Orange is modified code, and red is new code. This is the information we can extract from the version control system at a click. The second information source that I use in this presentation is test coverage, which we capture with coverage profilers, which run fully automatically in the background. And it tells us which code was executed when we ran tests, manual tests or automated tests. And this is again an example from the robot framework, method get time. And when a line is depicted with a green background, it was executed by the unit tests. And down here, there's parts or here that are depicted with a red background. So that means they were not executed by the unit tests. And typically when we see developers or test automation developers use test coverage, it's used on a very fine-grained level to see, are there any lines or any cases or any paths in the method I would like to test, and to check if I manage to test them with my tests. But much like the change tree map, I'm interested in lifting this information to the level of the entire system. This is the code coverage tree map for the robot framework for the unit tests. And this tree map depicts the entire Python code if we check out the robot framework. And the method is green if at least one line in it was executed by a unit test. It's a bit coarse because it could be that a large method is green, although many of its lines were not executed, but it gives us a good first impression. And one thing is, here's a big area that has a lot less code coverage than the rest of the system. And I have this specifically in here because a very important step whenever you do any code analyses is code discrimination. Because not all code is created equal, and not all code areas are of equal importance to the software system. And if we look into what this is, we see this is the libraries folder. And there's good reasons why you probably don't test the libraries as thoroughly as your own code, because the libraries are tested by many others, and we can probably assume that they work. So to see how thoroughly our own code is tested, let's exclude them. And now we get this tree map. Again, green means at least one method, at least one line in the method was executed by a unit test, and gray means not executed at all. Disclaimer, This is only the unit tests. We didn't run the acceptance tests. So this is not a criticism of there's missing tests. This is just as an example to show you how these analyses work. If you want to discuss the test coverage or the test gaps of the robot framework, let's take that offline, and I'm happy to chat about that. This is the code coverage example from the system I showed before. Gray means not executed in test, and green means executed in test. And in this picture, we see the aggregation of both automated tests and manual test cases. So this concludes the first part. Now that we have that data, what can we do with it? And the first question I want to focus on is, where are untested changes? Because we know what changed since the last release, and we know which code was covered by tests and which was not. And we can combine that information to see which changes were not yet tested. Why is that relevant? Because we know from research and also from intuition that those are the areas that are most likely to contain new bugs. And a so-called test gap analysis reveals those untested changes. I used the same tree maps, and to refresh, this was the change tree map between 4.1 and 5 for the robot framework. This is the code coverage for the unit tests. And if we combine that information, we get this picture. Gray means unchanged, independent of whether it was executed in testing or not. All the colored bits are the methods that changed since the last release, because we know them empirically to be the most error-prone areas of the system. Only if they are green were they executed by the unit tests. All the orange and red stuff is added and modified methods that were not covered by the unit tests. And I repeat, we didn't include the acceptance tests. So maybe those methods are tested thoroughly by the acceptance tests, maybe not. But the purpose of the test gap analysis is to show you, which areas did I not test with a certain test or with all the tests combined. I would like to come back to the example I showed before. Business information system, C#, 1.5 million lines of code. This is the tree map on the evening before the release was planned. And we see that there's a lot of changes in this area. Same day, test coverage of automated tests, unit tests and acceptance tests, and of the manual tests performed by a test factory in India, where a team had a lot of manual test cases they manually executed. And if we combine that information, we get this test gap tree map. Again, the colors mean the following. Gray means unchanged, independent of whether it was executed in tests or not. The colored bit is the modified code, and green means executed during testing. And what we're really interested in is to see, are there any big red components? Because this is tens of thousands of lines of code that were not tested at all in any of the test stages, not by automated tests, not by manual tests. And how can we interpret this? In the green areas, we don't know how many bugs are left, because we only know it was executed by manual tests. We don't know how thoroughly it was tested. However, for the orange and red areas, the inverse is as trivial as true. We can't have found a single bug because we never, ever executed this during testing. So the goal of test gap analysis is to allow us a conscious choice if we want to go into production with a software like this. And this team decided, no, they don't want to release it like this, but they want to do additional automated and manual tests for those areas before they ship it into production. So if we combine change information and test coverage information, we can see where untested changes are. However, we can also use that information about which changes were made and which tickets were fixed in the past to see where most bugs in the past were. And I want to give an example from a different system to show what I mean by that. This is a tree map of an industrial software system where every single rectangle is an entire file. And the intensity of the color corresponds to the number of times that file was touched when fixing a bug. So the whiter the file is, the fewer bugs were fixed in the last, I think, 2 years in this time. And the more intense the color blue, the more bugs were fixed in that file in the last 2 years. And we see here's an area that has a much higher fixed density than the other areas of the tree map. This tree map shows the test coverage. And you see, again, there's an anomaly here in the middle that shows us that there's much less test coverage here than in the other areas. And if we show those two tree maps on the same slide, it becomes apparent that in the area where there's the least coverage of automated tests, in this case, it's only automated tests, there's the highest defect density. So what happened here? This information is pretty trivial to extract if there's a build that runs automated tests and captures coverage, and if there's a version control system with at least for several years existing history. And I went with these tree maps to the team, and it turns out that this is the UI, and the rest is backend. And it turned out that they had never invested in the test infrastructure to make it easy to write UI tests. So as a consequence, there were much less UI tests than there were backend tests. And unsurprisingly, many more bugs slipped through that were in the UI than that were in the backend. And when we saw that, when the team understood that, they took the decision to invest into more test infrastructure for UI tests to close that gap. So this helped us with this team to identify the root cause and improve the test automation infrastructure. The last question I want to focus on is which tests should I execute now? And this is relevant for teams that have very large test suites that take hours or weeks to execute, and thus create a much too long feedback cycle between the developer introducing a bug and a test revealing that bug. Because ideally, I want that feedback cycle to be very short, when as a developer, I still know which change I did, still know the code. Because if it takes weeks or months to receive that information, it's much harder to do root cause analysis and to fix that. And for that, we work with test case specific code coverage. This is an example from a paint program, which has filters that blur or distort the image a bit. And again, a tree map, gray is a method, a rectangle is a method, gray means not executed, green means executed. And for this analysis, we measured the code coverage of every single test case. And this is the coverage of the Gaussian blur test. And this is the coverage of a different, in this case, test in create modify selection test case. And if we do that for the entire test suite, we can produce a lot of these tree maps, or in the back end, a lot of information about which test covers which areas of the code. And if you look here, you see that there are some test cases that are very similar. In this case, it's different tests for different filters. And there are some tests that have very different coverage. And we can use that information to optimize how quickly test cases can find new bugs. In this chart, we have the relative runtime to the right and the relative coverage on this axis. Relative runtime means 100% means we have executed the entire suite of automated tests. And relative coverage means we have achieved the code coverage of executing all tests. Unfortunately, in practice, usually tests are executed in the order in which they lie in the file system or package structure. And that means very similar test cases are executed one after another. And that means we get curves that are pretty flat. If we compute an optimal order, we get much more code coverage much quicker. And thus, if we decide only to execute a subset of the test suite, because it takes too long to execute all tests, then an optimized order is much better than the usual order we have in the test execution system. I have examples from open source systems. This is from different Apache libraries, Apache Maths and Apache Commons. And if we execute 1% of the test suite in the order in which it's usually executed in the system, we get like 3 or 4% of the code coverage. But if we compute the optimal order, we get 70% of the code coverage in 1% of the time. Now, what's that good for? Because code coverage doesn't buy us anything. We had research projects that used mutation testing, the artificial introduction of bugs to compute the mutation score. So the percentage of the introduced bugs that we found with the test suite. And it shows very similar graphs. So if we randomly introduce bugs, if we execute 1% of the test suite, we find 2 or 3% of the bugs. But if we if we spend 1% of the time it takes to execute the entire test suite and select those tests that execute the most coverage in this time, we find more than 70% of the bugs. In other terms, if it takes too long to execute the entire test suite all the time, we propose to have a subset selected like this, that you execute frequently, then you find 60, 70, 80% of the new bugs in a very short amount of time, and still execute the entire test suite maybe every night to find those remaining bugs that slip through the cracks. And to show another example from practice, this is from a customer who has, I think, 20 million lines of Java code in the system, 80,000 test cases that take more than 400 hours to execute and produce this coverage tree map, where you see that there's like 70% of code coverage. If we only invest 1 hour, but use the method I presented before to select the tests, we get this execution, which is more than half of what we get in 400 hours, in 1 hour only. And I think in this system, it would be a good idea to remove a lot of the redundancy in those historically grown 80,000 tests and focus the effort you free up with that you don't need to maintain the test suite, to focus on the areas that don't have any test coverage at all yet. If you're interested in speeding up your test suites, my colleague Fabian and I give a presentation free online on this on June 29. This is the link you can use to register that. Let me summarize. There's been a lot of research on test intelligence approaches that use version history information, ticket information, and test coverage information from your own system to help you be more effective and efficient in finding new bugs and then optimizing your limited test resources. And in case you're interested in this, please feel free to reach out. I can't be in Helsinki, unfortunately, but I would be very happy to chat either now in the remaining minutes or afterwards via mail or Zoom. Thanks, and have a great remaining RoboCon.
Next, we should have Elmar online. Elmar, can you hear me?
Yes. Hello, Antti. Good to hear you.
Hey, thanks for the awesome talk. I have first question for you. How's your knee?
Much better. Thanks for asking.
Good to hear. Good to hear. There's a ton of questions, so let's go through some of them. Is there an open source library to get such change tree map as you showed?
I don't know. Maybe it's an unpopular answer, but our business model is to sell licenses, but it's completely free for open source projects. And also the trial version is completely unlimited for 3 months. So if you want to toy around and try with that, you can try our tool. I'm not aware of an open source tool that creates those tree maps, but our code coverage profilers are open source too.
Excellent, excellent. Which languages of test objects do you support by that analysis? I think like programming.
Interesting question. And there's a two-part answer. We support the static analysis part, where we compute the changes for 25, 30 programming languages, pretty much all the popular languages there are. The test coverage part, we support for every language where you can measure coverage for. And we're working with customers with Java, C#, C, C++, Python, PLSQL, and others. The only one we've not managed so far is PL1. So I guess whenever there's a profiler, you can use these types of analyses.
Good, good. What is the best approach to increase test coverage of test acceptance in Agile Scrum?
I saw that question before, and I haven't yet thought of a good answer. I'm sorry. I think it depends too much on the project context and how the other tests look like, what the domain is, and so on. Maybe you can take the question to the coffee break and discuss it with others. I'm sorry.
That's a good answer. I think that's something to talk about during the next coffee break. How about manual tests? How did you manage and get the test impact of manual tests?
By having testers click when they start and when they end their manual tests. And depending on the manual test management tool, sometimes the manual test management tool has a button where you say, now I started and now I ended, and then we integrate it in that. And sometimes we simply deployed a very simple tool where the tester would select the test case she's executing and say start and end. So then we know, so then we can tell the profiler which part of the coverage corresponds to that manual test execution.
Good, good. Though all this is quite interesting, what is your concrete contribution to the open source community and how to apply the presented ideas?
I think it's twofold. As I said, we are a commercial company, but I think we have a twofold contribution to the open source community. The first thing is all our tooling is completely and internally free for open source. And the second part is that some of our tools are open source under the Apache license as well, namely the coverage profilers for .NET, which I think is the lowest performance impact profiler on the market. We extended Jacoco, and that's all for Java, which is obviously also open source. And we just released a very new JavaScript coverage profiler, which is also Apache open source.
Okay. One more question, or actually two questions. Is there some aid in helping me identify redundant tests?
Very interesting question. I think there's different ways. The first one is to do a static analysis and see if there's a lot of copy-paste programming between tests. I haven't spoken about that in the talk, but I did my PhD about copy-paste analysis, and we've done a lot of work on tests as well. And often that's the easiest way to find redundant tests because they're entirely copied. The second way would be to look at tests that have very similar coverage. The third way would be to look at tests that always fail or succeed at the same time. But all of these analyses give you candidates and not an answer which tests are really redundant. I think always a tester should look at them and decide, is the additional test worth the maintenance effort or the runtime expense, or can we delete it?
Exactly. One last question. How do you add business criticality to the change maps? So you basically could weigh that feature or whatever. Yeah.
We've thought about a lot, and we've thought about that question a lot. And we decided not to have another metric that weights that against that, but instead to use different tree maps for different critical areas of the system. And so sometimes we look at the entire system. Sometimes we look at only specific critical areas because we want to make sure that they are really covered. I think that's another example where it's really an expert support tool, not an expert replacement tool. The idea is to put all the data on the table and then have the experts decide which parts are how critical and which parts are maybe not so critical and can be lived without test coverage for the next release.
Thank you for the answers, and thank you for the inspiring talk. Let's give a big round of applause for Elmar. Thank you, Elmar.
Antti, thank you, and thanks for everybody who participated. I'll be in the speaker corner next.